Okay, hi. This is my video number 26. I'll talk on the Stokes theorems. Stokes theorem. Okay, so what is Stokes theorem? So basically, what we have done thus far is that we have learned how to evaluate the integral over the closed curve, and also we know how to evaluate the integral over the surface. Right now, if you combine those two under certain condition, of course, that's come up to the what we call a Stokes theorem. So let me give the detail of those things. So okay, so yeah, hopefully that's you can see clearly. Yeah, so let S be a piecewise smooth, be a piecewise smooth oriented surface, having a piecewise smooth boundary curve C, having a piecewise smooth boundary curve C, and we let F with component P, Q, R a function. Yeah, F is a vector field. Be a vector field. Be a vector field whose component have continuous first partial derivative. Yeah, whose component have continuous first partial derivative on an open region containing S, open region containing S. Then the circulation, the word here is circulation. Then the circulation of F around C in the direction counterclockwise with respect to the surface, unit normal, and so equal the integral equals the integral of cross F dot N over S, which is in mathematically we write that F dot dr, this is equal to integrate over the surface curl F dot N. over the surface S. Okay, and ds itself is f over dot m, where n is unit normal to the arc, unit normal to arc, surface arc. So what is this? So if you have, say, we have a surface, this is our surface. Okay, let's say that's our surface, and this surface form a boundary, right? So this is, we call it as a inside here, this is, we call it as arc. Okay, and this boundary here, this is how we call it as curve boundary C. That's move counterclockwise. That, and normal is a normal to the surface. So anyway, if you consider normal to the surface, it might be this point here, and normal to the region, it should be like that. So this, if you normal to that, this is normal to the surface. And if you consider the point here, normal to the surface is somewhere here. Okay. Now, if you consider C is a curve in XY plane, yeah, and R is a region in the XY plane bounded by C, then you can see that this equation can be reduced into the Green theorem. Yeah, if the region R or C on XY plane. Okay, I don't want to go that detail. I just want to focus on that. How to now give you a couple of examples. Example, how to use a Stokes theorem, yeah, to evaluate surface integral. First, evaluate S f dot n ds, where S is a surface x plus y plus z equal to 2 in the first octant. And given f is xz, yz, and xy. Okay, if you sketch the surface S, yeah, that will help us to find the limit of integration later on. So if you sketch this F, yeah, so it is not difficult to show that, to sketch that this is x, y, and z. In the first octant mean this part here. All right. So if you look at this, first consider on the axis. So x-axis, we have x, y, z 0. You put it there. Y, z 0, we get x equal to 2 here. And on the y-axis, xz is 0, so we got y equal to 2. On the z-axis, we have x, y 0, so z equal to 2. And then we consider on the each plane of this, yeah, to see how does the surface look like. So on the surface, on the plane xy, z equal to 0, so you can see when z equal to 0, xy equal to 0, so we have a straight line crossing x and y, x equal to 2. So we have this. Yeah, this is x plus y equal to 2. Now if you consider a xz, so xz from here, xz plane y is 0, so that gives you x plus z equal to 2. So that's, we have a straight line crossing x and y axis and intersect at equal to 2, z equal to 2. So we have that. Oh, we missed that. So that's 2 is there. Okay. And then the same thing if you on yz axis, x is 0, so we have y plus z equal to 2. So we have a straight line intersect yz axis at y2 and z2. So you can plot this, just continue that line. Oh, okay, better. So that's the line. So this is x plus z equal to 2, and this line is y plus z equal to 2. So this is your surface. That's your S. So this S, if you project on, look at from z positive, yeah, it will project on xy plane. So that give you, there's your arc. This is your arc. Okay, so we need this surface, we need this region, because we're going to use that as our limit of integration. All right. So let's work out on how to solve this, to evaluate this integral. So just fill up all those things, cross f. All right. This is, we have how to do this thing. I think I, j, k. We have del del x, del del y, del del z, and f. We have our f. Where is our f? Here. So we have xz, yz, and xy. I see many students when do the cross product, they don't put this I, j, k. As a result, when you write the outcome of curl, you don't have those I, j, and k. So you just put one line. Remember that for that we have 3 by 3 determinant of 3 by 3 vectors. So without that, so how can you find the determinant? So you cannot have basically. So you need those I, j, k. Yeah, many students did this. So now from here we can just find what is the element of each of those. So we have for I, del y, so we got x minus y. Yeah. For j we have z, so x minus y. So we have again x minus y. And for k we have x, that one 0, that one also 0, so we got 0. So that's our curl of f. Alright, and nds, this is given as, I think I have explained to you how to get this thing, minus fx minus fy 1 dx dy. Yeah, the reason because we project on the xy plane, so our function z is equal to 1. So basically we write z in term of function of x and y. Yeah, and then you can differentiate those, then you can have this thing. So then if you find this del f, so what is this? So from the given surface, yeah, from the given surface here, you have what? We have S, our surface S is x plus y plus z equal to 2. So you need to write z in terms of function of x and y. So we have 2 minus x minus y. So this is actually your fx y. Okay, so then we just differentiate this with respect to x. So we got minus x, say minus 1, and the negative we got plus 1. Then differentiate respect to y, we got minus, then again you got 1. So this gives you 1, 1, and 1 dx dy. And because we have negative here, of course from here you can find fx is negative 1, fy is negative 1. You substitute there, we have negative, negative, that give you positive. Okay, so therefore we have to integrate over cf dot dr. That gives us, we integrate over s cross f dot n ds. That gives us integrate those. So we have to fill up everything because we project on the xy plane. So now we have x from, look at this, our diagram here, yeah, x from 0 to 2, and y from this line, which is y from 0 into that, until that line, y equal to 2 minus x. So we have x from 0 to 2 and y from 0 to 2 minus x. Okay, and then you can just fill up everything there. So we got x minus y, x minus z, x minus y, z is 0, I can just put that, yeah, you can put 0 there, and then we have n ds is 1, 1, 1, 1, 1, 1 dx dy. So in this case dy dx, dy dx. Okay, and then that shouldn't be a problem for you to solve. X equal to 0 to 2, y equal to 0 to 2 minus x. That gives you x minus y. That gives you x minus y. So that gives you 2 minus 2x. 2x minus 2y. Right? That gives you 2x minus 2y dy. Dy dx. Okay, so I think you can solve this this problem. That give you what? So we have x from 0 to 2. We have 2x squared. We differentiate, integrate with respect to y. So we have 2xy minus this one is y squared dx. Y from 0 to 2 minus x dx. Then I think you can proceed this. You got whatever answer is. So to check your answer is correct or not, okay, for checking you can evaluate those cf dot dr using this is equal to, you can use C1 plus C2 plus C3, where C1, C2, C3, if you look at here, is this is your C1, you can consider this as C1, this is your C2, this is your C3. So you can evaluate the C1, C2, C3. So remember that C is the bounded S. Yeah, the boundary bound S. So we got S, then the boundary of S, that we call it S C1, C2, C3, not on the R itself. Okay, I'll give you another example. I hope I have, yeah. Let me give you another example. Let's say if I have surface S is given as x squared plus y squared plus z squared equal to 9, and our curve C is given as x squared plus y squared equal to 9 on z equal to 0, then f is y minus x. So again, if you look at this x square, everything, so should not difficult to sketch those diagrams. So you can see those for y, for x, so we have x, y and z. So on xy we have x squared plus y squared 9. This is a circle with radius 3. So on xy, so we have a circle of radius 3. That's it. And then on z axis, so we have again, it's like a sphere, right? A sphere. This is a circle there. So we have that. So my curve is not good. So that. Okay, so this is our surface. This is our surface. And you can see this is on xy plane. You can consider this as your region, and your C is given by that curve. All right. Now, if you use the Stokes theorem, we want to evaluate, integrate C f dot dr. So if you use the Stokes theorem, from Stokes theorem, so what we have, those C f dot dr, this is equal to, we have integrate over the surface S curl f dot n ds. So you need to find each of those things. That for the Stokes theorem. So you can try to solve this. So if you find the curl of f, that give you I, j and k, and we have del x, del y, del z, and your f is y minus x. So we have y minus x, this one is 0. Okay, so that will give you for x you got 0, 0, that's 0. For y you got 0, that one another 0, and for z you got minus 1, so you got minus 2. And you want to find the n. Your n is given as we have what we have is minus fx minus fy and 1. From the given s, that from the given s, so we have our s. Let me write here. Our s is x squared plus y squared plus z squared equal to 9. So from there we write z squared is 9 minus x squared plus minus y squared. Then you can have z equal to plus minus square root 9 minus x squared minus y squared. But it's given we need only the upper part of those, so we don't have the negative. Yeah, we remove the negative. Remove. Not really remove actually. We just take into account the positive part. Yeah. Consider only positive. Okay. This is your f. That gives you your f of xy. Okay. Then you can evaluate what is fx. From there you can find what is fx. Fx is you have negative square root. I think you got x over square root 9 minus x squared minus y squared, correct? You have to, yeah, I think so. And then you can find fy is given as you should have negative, you have negative here, right? Fy is a negative y over 9 minus x squared minus y squared. Then what we have, this is you can write this. This is your z actually y over z, because this is equal to z, right? So then you have this, you have that. Then this is n ds. That gives you dx dy. Then you can just substitute everything in there, and then we have integrate s cross f dot n ds. That give you, so we have that is integrate over s 0 0 minus 2, and then we dot n ds, which is this thing. We have minus fx, that give you x over 9 minus x squared minus y squared. Y, you got minus of fy, that give you y over 9 minus x squared minus y squared. Then we got 1 there, that dy, dx or dx dy. Okay, so that's isn't difficult to solve. So what we have now, I think I can just leave this to you. This is equal to integrate over a circle. Yeah, that's integrate over a circle. So you have basically the radius is 3, so you can take r equal to 0 to 3 and theta from 0 to 2 pi, because it's a full circle. We change that 9, that one give you r. So what you have here, 0 0, that 0, that 0, then got minus 2 here. Alright, so that gives you minus 2, and dy dx, that gives you r dr d theta. Then you can solve this thing. Right, then this gives you minus 18 pi. So hope that you can understand this thing. We choose a polar coordinate here because we integrate. The integration here involve x squared, y squared. We integrate, the region is on the xy plane where it is a circle. Yeah, a circle. This is your region of integration. Yeah. So it's a circle. So that's why we change to the polar coordinate. So we got this thing. So if you evaluate this, you can also got a minus 18 pi. Can you do this? So I just leave it to you for this to solve. You need to find what is your arc. Yeah. If you want to solve this, let me use another paper. So if you want to solve the same problem using line integral, so that we have integrate c f dot dr, we need to find what arc is from this circle here, from this diagram here. On xy plane, you can see that our x is given as 3 cos theta, yeah, because it's the radius of that 3, and y is given as 3 sin theta. And we know what else. Then we need then your r is given as x and y, so we have 3 cos theta, your y is 3 sin theta. Okay, then you can find what dr is. Your dr is, this is minus 3 sin theta and 3 cos theta d theta. Okay, then your f, what about your f? Our f here is given here. Yeah, our f, this is y negative x. That give you, your y is 3 sin theta, your x is 3 minus 3 cos theta. Therefore you can use that. So we integrate over a circle, that give you f dot dr, that will give you, so our f is here, dot dr, so that give you 3 sin theta negative 3 cos theta dot, your dr is this, that negative 3 sin theta 3 cos theta d theta, d theta, d theta. And then since we integrate over theta, now theta is, we have a full circle here, so which means theta from 0 to 2 pi. So it is much easier if you can find this, give you 18 minus 18 pi. So you give the same solution basically. Okay, yeah, I have some more example actually, but I think I just leave it to you to solve some of this example. Let's say, okay, I leave it as an exercise to you. Okay, number one, let's say verify the Stokes theorem. For we have f is minus 3y 3x and z4 and s is given as the top portion top portion of plane top portion of an ellipsoid 2x squared plus 2y squared plus z squared equal to 1 cut by z equal to 1 over sec 2. Okay, for this you should get the answer is 3 over 2 pi. And number 2, we verify Stokes theorem. Your f is given as z squared minus 2x y cubed, and s is a top portion of a sphere x squared plus y squared plus z squared equal to 1 cut by z equal to 0. And for this, the answer is minus 2 pi. Okay, so try to find another example. Okay, try this 1, 2, 3. We have many exercises here. So let's say your S, this is for maybe not this time. Okay, if you have F, just a minute. So S. Okay, so S is given as Z equal to x squared plus 4y squared, and cut by Z equal to 1. Okay, your F is given as y minus xz squared. Okay, so I think for this you can use x equal to cos theta, y equal to half sin theta, because this give you an kind of ellipse. Then z equal to 1, then you can find what r is, and so on and so forth. I mean, for this, the answer for this is minus pi. Let's try some more exercise for you. Number 3, number 4. Let's say we have f is equal to x squared 2x z squared, and bounded by your s is given by 4x squared plus y squared equal to 4. Next, f, we have 2y 3x minus z squared. Your s is given as x squared plus y squared equal to 9. And let me give one more. 4, 5, 6. Let's say f y z x squared y z x squared. Your s is given as x plus y plus z equal to 1 on the first octant. Okay, so I think with those couple of examples, it's enough for you to try to verify. Verify means you do both sides. Yeah, we integrate cf dot dr. This is using the Stokes theorem. We have s cross f dot n ds. So verify means we do this side, we do this side, both, and should give the same answer. So I think that's all for this video. Thank you. Bye.